We talk about energy all the time, right? I have no energy here. Let's save energy. But have you ever stopped to think about what it actually is? Well, that's what we're going to do. We're going to crack the code on one of the most fundamental ideas in the entire universe.
And Professor Brian Cox, he really hit the nail on the head. He said that because we use the word every day, its meaning has gotten a bit, well, woolly. So that's our mission today. We're going to take that woolly concept, unravel it, and get to what's really at the heart of it.
So, here's the plan. First, we're going to tackle that woolly concept head-on. Then, we're going to go hunting for where energy actually hides. After that, we'll uncover the one simple, unbreakable rule that governs it all. We'll see how it works in the real world. And finally, we'll get to the bottom of why some of it always seems to, go to waste.
Okay, let's dive right in. To really get a handle on this whole energy thing, which can feel kind of abstract, we're going to start with a really simple model. Think of it this way.
Okay, let's think about energy as money. Seriously, you keep your money in different places, right? A bank account, maybe some cash in your wallet. Well, energy works the same way. It's kept in different stores. And when you buy a coffee, you're just transferring money. Well, whenever anything happens in the universe, energy is just being transferred between those stores. And just like money has units, dollars, pounds, you name it, energy has a unit too. We call it joules. It's a surprisingly good way to think about it, isn't it?
So, if energy is like money, then what are these bank accounts? What do these energy stores actually look like in the real world? Come on, let's go find some of energy's favorite hiding places.
First up is the kinetic energy store. This one's easy. It's the energy of moving things. Think about a sprinter. The faster they run, the more energy they're stuffing into their kinetic store. It's that simple. More speed means more kinetic energy.
Okay, next up, the gravitational potential energy store. Imagine you've got a heavy box way up on a high shelf. It's just sitting there, but it has the potential to do something, right? Just because of how high up it is. That box has way more stored energy than the exact same box sitting on the floor. It's just energy waiting to happen.
Then you've got the thermal energy store. This one is super straightforward. It's just about heat. A steaming hot cup of coffee has a ton more energy in its thermal store than, say, a glass of ice water. The hotter something is, the more thermal energy it's got.
Now this next one is a huge deal. The chemical energy store. This is all the energy that's locked up inside things like food, fuel, batteries, you name it. It's just sitting there in the chemical bonds. And it takes a chemical reaction like, digesting your lunch or lighting a candle to unlock it.
And last but not least, we have the elastic potential energy store. This is a fun one. Anytime you stretch a rubber band or squash a spring, you are literally pumping energy into its elastic store. And what happens when you let go? Whoosh! That energy gets transferred somewhere else.
Okay, so now we know where energy hangs out, but there's one single, absolutely critical rule that governs everything about it. And I mean everything. It's a law of physics that, as far as we know, has never, ever been broken.
And the story behind this law is actually pretty cool. You have to go all the way back to the 18th century, to this brilliant French philosopher, Émilie du Châtelet. She was doing these experiments, dropping metal balls into soft clay. And she noticed something incredible. The energy the ball had because of its height didn't just vanish when it hit the clay. Nope, it was perfectly converted into the energy of its motion. It wasn't lost, it just changed.
And that amazing insight led us straight to what we now call the law of conservation of energy. And the rule itself couldn't be simpler. Energy cannot be created or destroyed. That's it. It can only be moved around, transferred from one of those stores to another.
So what does that really mean? It means there's a golden rule. The total amount of energy you have before something happens is the exact same amount of energy you have after it happens. Every single time. No exceptions.
Okay, that's the rule. But what does this unbreakable law actually look like out in the real world? Let's follow the energy in a classic example and really see these transfers happen.
Just picture a waterfall. At the very top, that water's just packed with gravitational potential energy. As it starts to fall, that potential energy gets swapped for the energy of motion, kinetic energy. Then, crash, it hits the bottom. But the energy doesn't disappear. No way. It just transforms again, this time into the sound of the crash and even a little bit of heat. The total amount of energy? It's exactly the same. It's just been shuffled around into different stores.
So how does energy actually make these jumps from store to store?
Well, it turns out there are 4 main ways. You've got mechanical working. That's just a force moving something, like you pushing a box. There's electrical working. Think of electricity flowing through a wire. There's heating, energy moving from a hot thing to a cold thing. And finally, there's radiation, energy traveling as a wave, like sunlight, or even the sound from that waterfall.
But there's a catch, and it's a big one. Even though energy is never ever destroyed, not all of these transfers are actually useful for what we're trying to do. And that brings us to the whole idea of wasted energy.
The official term for this is energy dissipation, and it's what happens when energy spreads out into the surroundings in a way that's just, well, not very useful. So when we say energy is wasted, we don't mean it's destroyed. It can't be. It just means it's been spread out, or dissipated, so it's really hard to get back and use for anything productive.
Think about your tumble dryer. It's a perfect example of this. The useful energy is the heat that actually dries your clothes, and the kinetic energy that tumbles them around. But what about all that noise it's making? That's energy escaping as sound waves. And what about the fact that your whole laundry room gets hot? That's also energy escaping as heat to the surroundings. See? The energy is all accounted for. It's just not all doing the job you want it to do.
And all of this leads to a truly mind-blowing realization. If that law is unbreakable, it means that every single bit of energy in the entire universe, the energy that's letting you think and breathe right now, the energy blasting out of our sun, the energy in a galaxy billions of light years away, all of it, every last joule was created at the Big Bang. It's all just been passed around, changing form, shifting from store to store for the last 13.7 billion years.
So that leaves us with one last massive idea to chew on. The energy that makes up you, me, and everything we can see. It's eternal. It was there at the very beginning of time. It's here right now. And it will be here forever, just changing and transforming. Which raises the ultimate question, doesn't it? If every joule of energy is eternal, where will it go next?